This is one of the classic practicals of physics, very, very important at the time, and it took a good many years to actually discover its importance. But this effectively can only be explained using wave theory of light. So what we're going to do is we're going to look at a laser and how we can basically prove its light. The only way it can be explained is using this light analogy. So what I've got here, massive laser. I'll just turn the safety on and turn it on. So it's a very high power laser. You can hear it roaring away. And what we're going to do is on this beam here, we need to think about safety. So I've got it ever so slightly tilting downwards, so you can't get it into your eyes unless you're actually kneeling on the floor. And what we're going to do is we're actually going to start putting in front of it these little slits. Now I'm going to move the camera around as we're doing it, but to start with I'm just going to slide it in front, and when we can get the laser through the slit from a distance, you should be able to see the pattern on here. Okay. Now this pattern changes depending on how close we put this to the screen. Quite a small pattern. As I move it further and further away, I'll have to adjust the height on it. Basically the rays, if I've got them there, have much more time to spread out. What's going on is our laser light comes in, it goes through a series of slits, in this case Young's double slit, so it's 2 slits, and what that does is it actually then spreads out into a series of patterns caused by the interference. So as the light comes through here, it interferes. In some bits it makes a brighter spot, and in some bits a darker spot. Now I'll move this closer up so we can see what's going on a lot bit more easily, and I'll adjust that. Now if I want to make some measurements, then I'm going to have to do that in a way that's nice and easy to do. If I was to take a very precise measurement tool, so for example here, millimeters and half millimeters on this scale, this would be dangerous because it's a reflective surface. So what I'm doing instead, I'm going to swap that around, and I'm going to use graph paper, and it's 2mm graph paper, so on that scale you can then start to see the size of the dots, the distance between the dots and so on. So here I have 2 slits that are 0.1mm apart, and what you can see is a whole series of dots. We have this central bright fringe, and then the first fringe, second fringe, third fringe, and likewise as we go the other way, so first fringe, second fringe, third fringe, and it just fades away. And it can only be explained by ripples of light, and as the ripples cross over they create those brighter, higher energy spots. If I move it a bit closer, then you can see the dots are much closer together, but again, as long as we know the actual distance between the screen and my diffraction grating and my pairs of slits that we've got here, then I should be able to do the calculations that Young did in the 1700s to prove that light must be a wave, solving a 200-year-old argument. If we change that, so put the dots that are actually 5 times further apart, then you should be able to see that those are much, much closer together. It kind of has the reverse effect of what you think. So go back to from the 0.55mm separation to the 0.1, and it gives them much wider spread. It's much easier to take those readings. Yeah. Now, what we've also got is what looks effectively a bit like plain glass, but actually is a whole series of slits. Now this one has 191 slits in every millimeter, so they're closer again, but there's lots and lots of slits, so you're letting through more light, so you get much brighter spots. Okay, so there's our central bright fringe, slightly less bright, slightly less, fading away more gently, but again you can see much more clearly because you're getting more ripples overlapping, much brighter spots, and much more definite dark fringes, okay, in the middle. So the bright fringe and the dark fringe, a very definite difference. Whereas if I go back to my double slit, then especially when you're looking here, you can start some just kind of fading in and out. There's not a definite dark spot. They kind of just slowly fade and then merge it, brighten up again into the next one. Okay, so that's the Young's double slit, and from that, by measuring different distances, we can very simply, using triangles, trigonometry again, by using those triangles, we can work out from that separation and the separation of the slits and the distance to the board, we can work out the wavelength of light, and we can do it really, really accurately. So if I change the colour of the laser, what I'll find is I will get the same behaviours, I'll get the same patterns, but the actual change will be in the distance. So if I take my red laser like I had before and play on both of them at the same time, then what you'll find is the separation between the green dots is much smaller. And the reason for that is you've got a smaller wavelength. So if I'm looking through my diffraction grating or double slit, a bit harder to see, but same patterning, you'll find you get the same effect. So the red and the green in this case will split up. If I had a white laser, what I would get in the middle there would be the mixture, try and get it through, excuse me, would be the mixture of all of the colours of light. So I get white in the middle, and then I would get the colours of the rainbow spreading out. Red would be on the furthest distance from there, so our first fringe would have red on the right, then it go through orange, yellow, green, blue, and if you had violet, violet there. So you get a spectrum going outwards from the middle, starting with violet. If we looked at the left-hand side, it would be exactly the same, but in reverse. So again, violet is diffracted the smallest amount because it has the higher wavelength, higher frequency, so it has a much shorter wavelength, so it has a much smaller angle. If I take that away, then you should be able to see this effect just with anything that we look through. So if you're looking through a diffraction grating, wherever you're seeing light sources coming in, you'll see those colours being split up. And we use that to actually break up and identify the colours of light coming from stars. So it's a really useful effect, and we shall study it again in year 13 in terms of how we look at stars and analyse their light, and therefore temperatures, distance and everything else. Okay, so crucial experiment because it's the only experiment that tells us that light is a wave, light is not any other form of energy. Okay, the diffraction gratings that we had before had parallel slits, so you ended up with a parallel ray of dots. What you'll find is if you're looking through materials that have more of a two-dimensional or even a three-dimensional structure like this material, this fine material, then what we end up with is when we shine the light through, we actually get that diffraction pattern happening not just horizontally but vertically as well. And again, the smaller the pattern that we have, the more that it spreads out. And as I change the orientation, you can see the orientation of the pattern changing. Now this is used to actually, with X-rays, so smaller wavelengths, but this is used to give us the patterns of proteins. It originally gave us the structure of DNA. So this crystallography, as it's known, this technique, is used to work out what the structure is inside things. And even when I look at different parts of the film, I'm still getting the same pattern. So it gives us layout as well by detecting the distance between all these things that are causing the diffraction. Separation of molecules, separation of atoms within a molecule, or complex molecules.